Hey everyone, excited to jump into a fascinating new area for our deep dive today. We're talking all about quantum computing and how it can be used for anomaly detection. Like finding a tiny imperfection in a seemingly perfect diamond or a fake painting hidden among masterpieces. It's about finding those needles in haystacks of data. And what's really cool is that we can use the power of quantum computers to do this even better than ever before.
Yeah, that's a great way to put it. We're really talking about using the unusual, almost counterintuitive world of quantum mechanics to solve problems that affect us every day.
And speaking of cutting-edge research, today's deep dive is taking us straight to a paper titled The Role of Data Embedding in Quantum Autoencoders for Improved Anomaly Detection.
Quite a mouthful, right?
It is, but trust me, the concepts are way cooler than they sound.
Hmm.
And the researchers behind this work come from some really prestigious institutions, the Thomas Jefferson National Accelerator Facility and Durham University.
They're really doing some groundbreaking stuff.
So before we get too deep into the weeds, let's start with the basics. For those of us who aren't quantum physicists, what exactly is a quantum autoencoder?
Okay, so imagine you're taking a digital picture and shrinking it way, way down to its absolute bare essence, almost like a fingerprint of the original image. But then you can perfectly recreate that original picture from just that tiny fingerprint. That's essentially what a quantum autoencoder, or QAE, does, but instead of working with pixels, it's working with data in the realm of quantum mechanics.
Okay, so it's like teaching a computer to recognize patterns, but doing it using the rules of the quantum world instead of our everyday classical world.
Exactly, and that's where data embedding comes in. It's about how we translate the information we want to analyze into a format that a quantum computer with its qubits and superposition can actually understand and work with.
So it's kind of like choosing the right language for the quantum computer to understand, right?
Exactly. We have to speak its language. And this paper really dives into how different ways of preparing or embedding that data can drastically affect how well the QAE can actually detect those anomalies.
Okay, that's fascinating. So it's not just about having a powerful quantum computer, it's about how we communicate with it, how we
Mm.
translate our data into something it can actually work with.
Absolutely. And what the researchers explored in this paper were some specific data embedding techniques like data re-uploading and parallel embedding. They wanted to see how these methods impacted the QAE's performance, how accurately it could spot those anomalies.
Intriguing. Those terms sound pretty complex, though. Could you maybe elaborate on what those terms actually mean and how they work in practice?
Sure, so let's break down these techniques a little. First up, we've got data re-uploading. It's kind of like, imagine you're learning to play a new song on a piano. You practice the same scales and arpeggios over and over again. It can seem a little repetitive, but that repetition is what helps you internalize the patterns and make them second nature.
So it's about giving the quantum computer that same kind of repeated exposure to the data to solidify its understanding of what's normal.
You got it. With data re-uploading, we're essentially feeding the same data into the QAE multiple times. But here's the quantum twist. Each time the information is processed a little differently due to the probabilistic nature of quantum mechanics.
Interesting. So it's like those subtle variations help the QAE develop a more complete and nuanced understanding of the data.
Exactly. It's not just rote memorization. It's about building a more robust representation of the underlying patterns in the data.
That makes sense.
Yeah.
Now, what about this parallel embedding? That one sounds even more mysterious.
It's a bit more complex, but think of it this way. If you were trying to explain a concept like freedom to someone, you wouldn't just use one word, right? You might use metaphors, examples, stories, different ways of approaching the idea to convey its full meaning.
It's like you're trying to paint a richer, more multidimensional picture by using multiple perspectives.
That's a great way to put it. And that's what parallel embedding does. It feeds different aspects or representations of the data into the QAE simultaneously. It's like giving it multiple lenses to view the data through so it could pick up on nuances and patterns that it might miss with just one perspective.
So it's like giving the quantum computer a whole toolbox of different ways to analyze the data rather than just one tool.
Exactly. Now, the researchers in this paper, they didn't just stop at theory. They actually put these techniques to the test.
Always a good thing.
Right.
Yeah.
So they started with some simpler data sets. Think geometric shapes like circles and squares. They trained the QAE to recognize the normal shapes and then threw in some anomalies like an oval or a dented circle to see if it could tell the difference.
So it's like showing a child a bunch of round cookies and then slipping in a square cracker. Can they
Uh,
spot the odd one out?
Precisely. And what they found was that this data re-uploading significantly improved the QAE's accuracy in spotting those weird shapes. It was like those repeated exposures really helped it hone in on what a normal circle should look like.
So even with simple shapes, how you prepare the data for the quantum computer makes a big difference.
A huge difference.
Yeah.
But of course, the real test was to see how these techniques would hold up in a more complex real-world scenario. And for that, they decided to tackle a problem we're all familiar with, credit card fraud.
Ah, yes, the classic needle in a haystack problem, but with real financial stakes. So they were trying to teach a quantum computer to become some kind of fraud detection super sleuth. So did they actually pull it off? Did they create a quantum-powered fraud fighter?
Well, that was the hope, right? They took a massive data set of legitimate credit card transactions.
Yeah.
All the everyday purchases people make, groceries online, shopping, those sorts of things.
Feeding the QAE a taste of normal spending, so to speak.
Exactly. And from that beta, the QAE was able to learn those typical patterns of how people use their credit cards, the amounts, the frequency, where they're making purchases, all those little details.
Like building up a digital fingerprint of normal financial behavior.
Right. And once they had that baseline established, they hit the QAE with a new data set. This one laced with fraudulent transactions. Those sneaky attempts to make off with someone else's money.
The moment of truth. Could the QAE sniff out the scammers?
That's the question. And what they found was fascinating. Both data re-uploading and parallel embedding, those techniques we talked about, they consistently outperformed the standard approach to anomaly detection. The QAE was able to pick out those fraudulent transactions from the sea of legitimate ones with much higher accuracy.
Wow, so those techniques actually made a tangible difference.
They really did. And it makes sense if you think about it. Giving the QAE that repeated exposure through re-uploading, letting it see the data from different angles with parallel embedding, it all adds up to a more sophisticated understanding of what's truly anomalous.
It's like giving our quantum detective a much keener eye for spotting those subtle signs of foul play.
A great analogy. And this has huge implications, not just for credit card companies, but for any field where spotting those rare events, those outliers in the data, is crucial.
Absolutely. We're talking about everything from cybersecurity to healthcare to even things like predicting earthquakes.
Exactly. And what's really exciting is that we're just scratching the surface of what's possible with quantum computing and anomaly detection. This research is really a proof of concept. It shows us what might be achievable as we continue to develop these techniques and refine our quantum algorithms.
It's like we've opened a door to a whole new world of problem-solving, one where we can harness the strangeness of quantum mechanics to tackle challenges that have seemed insurmountable before.
Precisely. And the most important thing is to stay curious. Keep asking those what-if questions, because who knows what other breakthroughs are waiting to be uncovered in this incredible new frontier of quantum computation.
Couldn't have said it better myself. So as we wrap up this deep dive into the world of quantum anomaly detection, let's all carry that sense of wonder and possibility with us. Thanks for joining us on this journey, and be sure to tune in next time for another exciting exploration of cutting-edge tech.